Welcome to today's explainer, everyone. I am absolutely thrilled to guide you through this one because, well, we are about to embark on a journey to the unimaginably small. We're literally shrinking down to a microscopic level where the traditional everyday rules of physics just fundamentally change and entirely new, almost magical properties start to emerge. So get ready because we are exploring the wild and fascinating world of low-dimensional materials.
Okay, let's just dive right into this. There's a really famous quote that perfectly hits the nail on the head regarding why this topic is absolutely crucial. It goes, "Those who control materials control technology." And, we aren't just talking about finding new rocks in the ground here. We're talking about the ultimate frontier of human engineering, the ability to control and manipulate matter right at the atomic scale. That is exactly what's going to define the next century of technological breakthroughs, covering the whole shebang from medicine to quantum computing. But to really grasp this frontier, we first have to wrap our heads around this scale. Just look at that number, 1 billion. When we talk about a nanometer, we are talking about exactly 1 billionth of a meter. It's a scale so unbelievably microscopic that our standard everyday intuition about size just completely breaks down. And that's the incredibly tiny realm we're journeying into today. Here is our roadmap for today's explainer. First, welcome to the nanoscale. Second, the Nanomaterials Zoo. Third, dimensions, 0D to 3D. Fourth, shapes and structures. And finally, why size matters. Section 1, welcome to the nanoscale, grasping the unimaginably small. To really understand what unimaginably small actually means, I want you to imagine taking your everyday world and shrinking it down by some pretty mind-bending fractions. Let's put this into perspective. If you start with a normal house, roughly 10 meters wide, and you shrink it down by a factor of 100,000, you get down to the diameter of a single strand of human hair, which is about 100 micrometers. Now take that tiny single strand of hair and shrink it down another 100,000 times. That brings you to a 1 nanometer diameter. A single-walled carbon nanotube lives right at this scale. Think about that. It's 100,000 times smaller than a human hair. No way, right? So, what officially qualifies something to be a nanomaterial? It's actually a super strict boundary. A nanomaterial is defined as a material in which at least one dimension, so length, width, or height, is less than approximately 100 nanometers. Alternatively, it can just be a material that has an average grain size of less than 100 nanometers. That 100 nanometer threshold, that's the magic line we cross to officially enter this totally unique scientific domain. Real quick, before we look at specific materials, let's parse out some vital jargon you're definitely going to encounter. At this scale, matter tends to clump together in a few different ways. A particle is just a defined, minute piece of matter. Simple enough. But when particles gather together, they form either agglomerates or aggregates. An agglomerate is a collection of weakly bound particles, so they're really just loosely hanging out together. An aggregate, on the other hand, consists of strongly bound or totally fused particles. They are essentially welded together. Section 2. The Nanomaterials Zoo, Carbon and Semiconductors. Now that we've got our definitions down, we're going to focus on two of the main exhibits in our microscopic zoo, carbon-based materials and metal or semiconductor-based materials. These two categories are just totally different beasts. Carbon-based materials, for instance, typically take the form of hollow spheres, ellipsoids, or these really incredible cylindrical tubes known as nanotubes. Semiconductor quantum dots, however, are a whole other story. Instead of hollow tubes, a quantum dot is a closely packed crystal made up of hundreds or even thousands of atoms clustered together, usually sitting at just a few nanometers wide. Let's look a little bit closer at carbon, mainly because the sheer versatility of nanocarbon is just astonishing. Depending on exactly how you arrange the carbon atoms, you get entirely different materials. These are known as allotropes. For example, you have flat single-atom sheets called graphene. If you roll that flat sheet up into the smallest possible tube, boom, you get a nanotube. Curl it up into the smallest possible sphere, you get a fullerene. Actually, fun fact about the C60 fullerene, its molecular ball structure of pentagons and hexagons looks exactly like a geodesic dome. That's actually why it was named after the famous architect and inventor, R. Buckminster Fuller. Section 3. Dimensions, 0D to 3D. The dimensional descent. Let's see how all this builds into an entire classification system. We are going to take a literal dimensional descent here, organizing these materials from 0 dimensions all the way up to 3 dimensions.
Okay, playing tour guide for a second here, this whole classification of low-dimensional materials depends entirely on how many dimensions are confined below that magic 100 nanometer limit we talked about earlier. If all the spatial dimensions are trapped in the nanoscale, it's 0D. If just one dimension is allowed to grow larger than 100 nanometers, it's 1D. Two dimensions growing larger makes it 2D, and if all three dimensions grow beyond that limit, well, then it's a 3D bulk material. Let's look at how this plays out visually. At 0D, every single dimension, length, width, and height, is measured within the nanoscale. There is absolutely zero room for the material to stretch out past 100 nanometers. Everything is totally locked in. Great examples of this include the fullerenes we just talked about, colloidal particles, and quantum dots. They're basically just tiny, confined dots of matter.
Now, if we give the material just one dimension to grow past the 100 nanometer mark, we enter the 1D realm. Because it can only stretch out in one specific direction while the other two stay strictly confined, this naturally leads to microscopic needle-like shapes. This is exactly where we find structures like nanowires, nanofilaments, and those famous carbon nanotubes. Moving on, if two dimensions manage to escape the nanoscale, we get 2D nanomaterials. Because they can freely grow in length and width, but their thickness remains permanently trapped below 100 nanometers, they form ultra-thin plate-like shapes. Think of things like nanofilms, nanocoatings, and graphene. Graphene is actually just a single, flexible, lightweight, but incredibly strong 2D sheet of carbon. And here's the wild part. If you just endlessly stack those 2D graphite sheets right on top of each other, you actually get everyday 3D graphite. Which perfectly brings us to 3D bulk nanomaterials. Here, none of the dimensions are confined to the nanoscale. They're macroscopic objects. But, and this is a really crucial but, they are still considered nanomaterials if they are built from a multiple arrangement of nanoscale crystals, usually packed together in a bunch of different orientations. So it's bulk material, for sure, but it's engineered from nanoscale building blocks. Section 4. Shapes and structures. Morphology and composition. Now let's transition from those basic dimensions to the incredible, almost sci-fi level shapes and structures these materials can take when scientists engineer their morphology and composition. So scientists generally classify the morphology, which is just a fancy word for the physical form, of these structures primarily by their aspect ratio. This basically divides them into two main camps: high aspect ratio particles, which are long and stretched out, versus low aspect ratio particles, which are much more compact and uniform in their dimensions. And let me tell you, the architectural variety here is truly fascinating. When we're engineering at the atomic scale, we aren't just stuck making basic spheres and tubes. We are literally building nanohelices that spiral like microscopic springs. We've got nano zigzags, we are erecting nano pillars, weaving nano belts, and forging these highly compact nanopyramids and nanocubes. It is quite literally structural engineering at the atomic level, and it is awesome. Now, what's really interesting here is the composition aspect. We don't just have to use a single material, though obviously we can, creating solid compact shapes or hollow nanospheres. We can also build composites made of two or more materials. Scientists can actually engineer microscopic composite barcodes made of alternating strips of different materials. They can even create these crazy encapsulated spheres featuring a solid outer shell that protects a tiny liquid oil-filled core, and the whole thing sits well below 200 nanometers. Section 5. Why size matters. The quantum realm. All right, this leads us to the ultimate question, really the climax of our explainer today. We've seen the dimensions, we've seen the amazing shapes, but why? Why go through all this immense trouble to manipulate materials into these specific microscopic shapes and sizes? Why does size actually matter so much? To understand why this is so revolutionary, we really have to bridge the gap between structural chemistry and totally mind-bending quantum physics. I want to pose a question to you. What happens to electrons when we strip away their physical space? What happens when they literally just have no room left to move? Well, the answer lies in something called the density of states. Simply put, this is the number of energy states available for electrons to occupy. In normal, everyday, bulk 3D materials, these energy states are continuous. The electrons can just flow freely. But when you shrink the material down and essentially trap those electrons in the nanoscale, their available energy states become discrete along the direction of confinement. They can't just flow continuously anymore. They are quite literally forced into very specific discrete energy levels. And so here is the absolute crucial takeaway. When the physical spatial dimensions of a solid are shrunk down so incredibly far that they match the natural wave size of its own electrons, which physicists call the de Broglie wavelength, normal classical physics just steps aside and quantum effects completely take over. Shrinking matter isn't just about saving space. By confining these electrons, we unlock entirely new, highly controllable thermal, electrical, and quantum properties. The old rules change, and we get to write the new ones. It really leaves you wondering, with the ability to engineer custom properties, atom by atom, what totally new, impossible technologies are we going to build next?